Okay, so let's now apply the integral transforms to derive the Box-Mahler method. So Box-Mahler method is a method to sample standard normal variables and two in parallel. So we are sampling x and y, they are independent standard normal random variables. And while we had this integral transforms, I told you it's a method to derive the Box-Mahler method. And so we in the following we are looking always at the expectations of a function applied to the two independent standard normal random variables. So g is the measurable and bounded function from R2 to R. And well, x and y are supposed to be independent and standard normal. So its densities, its joint density, it's a product of the marginal densities, and in this case we get 1 over 2 pi e to the power minus x squared plus y squared divided by 2. So if you have independent random variables, the joint density is a product of the marginal densities. And so what we can do, we can write this expectation here as the integral of the function with respect to the density. So why does it help for deriving the method? So g is measurable and bounded. So g can in particular can be the indicator function of an arbitrary measurable set, and by looking at this we are checking whether we have the right probabilities. And if we have the right probabilities always, then we have found the sampling method for the variables we wanted to have. Okay, so we have now this expression here for the integral. So how can this help to derive a sampling method? So we will apply two coordinate transforms, and the first one is the polar coordinates transform you have seen in the previous example. So instead of integrating over R2, we are integrating over 0 to infinity and 0 to 2 pi. And x is replaced by r cosine phi, y is replaced by r sine phi. So if x is this, y is this, well, we can also compute x squared plus y squared. So it's r squared cosine squared plus r squared sine squared, and cosine squared and sine squared is 1. So only the r squared remains. And then we have this term r here. That's the correction term which comes from the Jacobi determinant. And here we have also used simultaneously Fubini's theorem to exchange the order of integration, but that's not the main point here. So we are using the polar coordinates transform to rewrite this expression as this expression. So because integral transforms, well, can be a bit messy, so let's break it down in a bit more detail. So here it's again written down our polar coordinates transform. So here with open sets and open sets, and here we are missing something from R2, so this line, this strip, but we call so changes of the integrand or lower dimensional subsets do not influence the integral. So this is our T1. We already have computed in the previous example the Jacobi matrix, and this is the determinant of the Jacobi matrix. And okay, so let's look at the changes of the integral again. So T1 is our transform given by this relation, and the magenta stuff is the Jacobi determinant. So let's first deal with the red. So we are exchanging R2 with the integral from 0 to infinity, 0 to 2 pi. That comes from mu and v. The blue is is exchanging the coordinates x and y with respect to r and phi, and that's here the changes in the coordinates. So x is r cosine phi, y is r sine phi, and here we are instead of x squared plus y squared, we are getting r squared. And the magenta stuff is a Jacobi determinant. So this breaks it down into pieces what was going on. Okay, but how should this help to come up with a sampling method? So for this we need another transform. So this we have derived, and there's another transform coming, T2. and exchanging the integrals with Fubini. What's T2? So here we have an integral from 0 to 2 pi and 0 to infinity. And T2 breaks it down to 0, 1, 0, 1. Why 0, 1, 0, 1? Well, 0, 1, 0, 1 smells a bit of independent and uniformly distributed random variables on 0, 1. But what's T2? T2 maps from 0, 1, 0, 1 to 0 infinity 0 to pi, and u is mapped on the square root of minus 2 ln u, and v is mapped onto 2 pi v. So in the second coordinate we have phi ranging between 0 and 2 pi, and if we have the 2 pi here and 2 pi here, we can go from 0 to 1. Okay, that's the easy transformation somehow, the easy part. Then we have here r ranging between 0 and infinity, and if we have the square root of minus 2 ln u, well, the ln of 1 is 0, and the ln of 0, well, this is not defined, but for x going to 0, ln x goes to minus infinity. So by this transform, we are, instead of 0 infinity, we have 0, 1. So, but of course there are many more maps which map 0, 1 into 0 infinity. But this here, by some clever imagination, this part here is the right transform which removes all this here, all this part here, which comes from the Jacobi determinant first, or the r comes from the Jacobi determinant first, the e comes from the density, and by using T2 and the integral transform, this part is removed, and this is the really clever thing about this second step. But as before, this will be broken down in a bit more detail. So this slide is for the main ideas of the second step. So we have now this integral 0, 1, 0, 1 g square root of minus 2 ln u cosine 2 pi v, and here square root of minus 2 ln u sine 2 pi v du dv. Okay, and integral 0, 1, integral 0, 1, no factor. So this is in fact the expectation of g of, and now in the first component here and the second component here, we have now a random variable capital U, which is uniformly distributed in 0, 1, and here instead of the small v we have now the large v, and it's also uniformly distributed in 0, 1, and both are independent. So with this clever second step, we can rewrite this in this form, and this is just the expectation of this of g applied to this transform of two independent random variables which are uniformly distributed on 0, 1. So with this step here, well, we have accomplished our task, because this is valid for arbitrary g's. So this random variable here and this random variable here, they have now the same distribution as x and y, so they are independent standard normal random variables. And well, this is done now by T2. T1 was the preparation, and T2 does the final job. Okay, but now let's break down how we come from here to there. So this is the transformation in detail, and well, to validate the step, we have now to compute the partial derivatives. So first we have to differentiate this with respect to u and v. With respect to v, it's simple, it doesn't depend on v, so here we have a 0. And here, well, we have to differentiate this with respect to u, so we need to know how to differentiate the square root, the logarithm, and we need to know the chain rule, and by elementary computations we get this. The second component is even simpler. Differentiating with this with respect to u, we get a 0, and with respect to v, we just get a 2 pi. So we have this Jacobi matrix, and this is the determinant, so this times this minus this times this. So this is the determinant of the Jacobi matrix. And now again with colors, So once again, 0 infinity, 0 to pi is now 0, 1, 0, 1 by the definition of u and v. Blue is the exchange of the variables. Instead of r and v, we have now this expression with u. Instead of r and phi, we have now this expression with u and v. So instead of r, we have always minus 2 ln u and the square root of it. So here and here. Also, and instead of phi, we have 2 pv, and here we have also 2 pv. And now how to get rid of the magenta stuff. And here, well, that's the cleverness of this transform. So the Jacobi determinant reads as this. But here you can see, here we have square root of minus 2 ln u, which we have already here. So square root of minus 2 ln u is r. And by calculating, one also sees that u is e to the power minus r squared half. So the Jacobi determinant is just accepts this factor 2 pi here, or the inverse of this. And if we also take this one into account, so the Jacobi matrix is just the inverse of the thing which we want to remove. So applying the integral transform theorem, we're getting from here to there. And that's what we are doing in the second transformation. Okay, so here's a summary of this previous steps. So that's the proposition which summarized Box-Mahler. So u and v are two independent random variables, uniformly distributed in 0, 1. If we define x in this way and y in this way, then x and y are two independent standard normal random variables. So we need to be able to sample from this. We need to be able to compute the logarithm, the cosine and the sine and the square root. And then we have our algorithm for generating samples from the standard normal distribution. And you can see here from proposition 6.2 to algorithm 6.3, well, there's nothing going on. So it's easy to implement this. An alternative is Marsalia's polar method to this sampling method. What's Marsalia's polar method? It's very similar, it's related, so its proof will be an exercise. So here we start not from a uniform distribution in 0, 1, but x and y are, which is our starting point here, they are uniform distributed on the unit circle. So for technical reasons, a unit circle without 0, 0 and without the boundary. But for sampling this, again, lower dimensional subset don't matter. So here's the Lebesgue density of x and y. So it's just the indicator function of b, and with a normalizing factor 1 over pi. So x and y is uniformly distributed on the unit circle. And what's the next step? So we square the coordinates, sum them up. So we are computing the squared distance to the origin, and then we are building this expression. So square root of 2 ln r divided by r, and for z1 we multiply it with x, for z2 with y. So first component, second component. And then z1 and z2 are independent standard normal random variables. Well, that's an alternative. How to derive this? Well, it's again clever use of integral transforms. So if you want to solve this exercise, well, you can use similar transforms as for deriving Box-Mahler method, or you should use. And if you struggle a bit, well, just Google Marsalia's polar method and you will get a lot of advice. And the advantage is here, so here we do not need to evaluate sine and cosine. So here are no sines and cosines. But on the other hand, we need to be able to sample from the uniform distribution on a circle. And this can be done, for example, via acceptance rejection sampling, which we had in the first lecture. So we are sampling independent and uniformly in -1, 1. So this covers the unit circle, and if the sample falls into the unit circle, then we keep it, and if not, we reject it. And if we keep it, then this line here does the Marsalias polar step. So this is just written in a bit different way what is written here. So also Marsalias polar method is easy to implement, while we have now this additional acceptance rejection step, but no sine and cosine. Okay, so this was Marsalias polar method. Before we had Box-Mahler method and the approximate ITM. And next lecture we will discuss the cigarette method, which is a really fancy and elaborate method, and it's a standard from MATLAB. Okay, that's all for lecture 6.